When you're cleaning, do you ever stop to think about where the sponge comes from? I don't mean where you bought it or how your modern sponge was made. But what about the origin of a sponge? A sea sponge. But did you also know that there are sea sponges that are hard? Some of them are even made of glass, and definitely not the kind you'd want to be scrubbing and cleaning with. How does something made of glass survive at the bottom of the ocean? And what can that teach us about designing better materials and structures? Let's dive in. This is ASU. This is a Venus flower basket. It's a deep sea sponge that is primarily made of glass. This lattice structure with its tiny strands is basically glass. How is something that ought to be fundamentally so brittle survive in deep sea conditions? We decided to study the sea sponge using X-ray tomography, commonly referred to as micro-CT scanning. One of the more remarkable things of the Venus flower basket is that while it is primarily a lattice, not every node of the lattice is fully connected. In fact, some of the nodes have beams that sit on top of each other, like a woven structure. That gave us the idea of decoupling nodes selectively in engineering lattices, like the body-centered cubic or BCC lattice, and making an interwoven or IBCC lattice. We then 3D printed lattices like these with different shapes and set about asking how the decoupling of nodes would influence their mechanical behavior. One way to do this is to compress these lattices and study how they respond, which we do by measuring the reaction force that the lattice exerts when subjected to a displacement. Our results showed that the interwoven lattices are remarkably less stiff or more compliant than the fully connected lattice. We conducted simulations to try and understand why, and found that this is because decoupling the nodes reduces the localization of internal forces in the lattices. In other words, it distributes the force each lattice beam experiences more uniformly. We then showed this for several other lattice shapes, finding that decoupling nodes can increase compliance in many different kinds of shapes by as much as 5 to 20 times. In fact, our interwoven lattices exhibit some of the highest compliance or least stiffness for a given mass ever reported in the literature. Now, why does this matter? Think about applications where we'd like to have structures compress a great deal while also absorbing as much energy as possible. Helmets, crash-absorbing structures in cars or helicopters. Think about sensors that detect small amounts of deformation, maybe for detecting changes in breathing patterns or for absorbing energy from ocean waves for energy harvesting in batteries. In all these situations, what we want is something that is very dense but can also deform as much as possible for small loads. And that is where these structures can prove to be vital. If this is what we can do with one design principle from one biological organism, imagine what all we can accomplish if we unravel the very structure of life. As the example of the Venus flower basket shows, the underwater world continues to inspire. It's not just the beauty of a coral reef or the practicality of using a sponge as, well, a sponge. The structures found there provide an ocean of possibilities for modern materials. This was ASU. Thanks for watching.